Warm welcome, everyone. Great to see you all. Great, Frederik, to see you. Good morning. Thanks for coming. It's a great pleasure to introduce Frederik from Ende, who's speaking today in our seminar. So he's been working at TU Munich with Thomas Schulte-Herbruggen, who we love for his very pedantic views on notions of quantum control and reachability, and this is meant as a compliment. And we will hear some of this gospel of reachability in controlled Markovian systems also today. So this kind of spans a wide range of topics in mathematical quantum information, in control, in quantum thermodynamics. So that sounds all very exciting. Thanks for coming, at least electronically in these still somewhat awkward times, although things become better. I was actually attending an on-site meeting just yesterday. Yeah, that's great. Thanks again, and I would say the stage is all yours.
Well, thank you very much, Jens, for the kind introduction. Yeah, indeed, as you've said already, with today's talk, I'll try to cover a variety of topics and how they kind of go together, and the touching points between them, at least in terms of what I am looking at currently, and I was looking at over the last few years during my PhD, which I actually finished end of 2020 already. And indeed, the question of reachability is one of the most fundamental one in quantum control theory. I mean, it's also a very intuitive question, asking, well, I have my system, which I can, let's say for some reason, I know I can describe it by some Markovian dynamics, whatever that means for now. And I know it's currently in the state A, and which states can I generate if I can influence the system by means of some like magnetic fields or lasers or however I can influence it, really. So that's a fundamental idea of reachability as part of quantum control theory. This is what the first part of this talk will be about. And in the second part, as Jens also said, we'll go to we look at connections to quantum thermodynamics, which emerge quite naturally from the questions we will be looking at, but one step at a time. So just so we're on common ground here, what do we mean if we say reachability mathematically? I mean, there's an intuitive idea behind it, but if we want to prove results, we should have a rigorous framework which we're working in. So as you all know, one starts with the Liouville von Neumann equation for closed systems. If your system is generated by a Hamiltonian and you can guarantee that the system is shielded well enough from the environment such that the evolution is unitary, then the dynamics is generated by this equation right here. So here I have this notion of the trace class. For most of the talk, as it will be in finite dimensions, we don't have to care about that. There will be a small portion in infinite dimensions where all you have to know, if you're not familiar with it, is that the trace class is the largest class of operators where something like the trace makes sense. So just to ensure mathematically that what we're talking about, it works really. It's all we're doing here. So this is closed system dynamics. There's no control here yet, and one usually models this one way to model this is by control Hamiltonians and control amplitudes. So this could, for example, be the amplitude of the magnetic field, which I'm subjecting the system to, and this interaction is modeled by this control Hamiltonian Hj.
So just to be sure, so like the input of the problem is the Hamiltonians Hj, which are kind of given and kept fixed, right? And then you will presumably have like further constraints on the control functions Uj in some way, but the Hj is like set in stone once and for all, correct?
Right, yeah. So in advance, I say I have these types of controls. These are the Hj, and what I can do is adjust the control amplitudes. For a lot of applications, one usually kind of caps the control amplitudes because you can't have infinitely strong controls, but for mathematical purposes, just to have the easiest possible scenario, which still in a lot of cases is very difficult, especially once open dynamics come to play. Usually one starts with, well, these uj can be any L1 functions, can even be unbound in theory, just so we can not an immediately hard time answering these questions. But yeah, so that's a setting. This is the control level for Neumann equation. Of course, one can look at this as kind of a mapping, or as a black box, which takes some kind of control inputs, control functions, and outputs a state, the final state after these controls have been applied, together with the natural dynamics, obviously. And the question is, which states, given some initial state, can I generate, can I reach, or can maybe reach approximately? But yeah, okay, we'll come to that. So now, as you also all know, for a lot of applications, there's like you can't really talk about closed dynamics. You cannot shield off the environment effectively. And the easiest way to implement system-environment interactions via Markovian dynamics. This, although it doesn't cover every physical system out there, it does cover a lot, and especially enough to look at this theory mathematically. So this is the uncontrolled.
Not all dynamics is ultimately truly Markovian, and this.
Right now, if we have Markovian dynamics, and this gamma, this interaction terms of a very specific form, called the GKSL form, Greenlee, Kozakowski, Sudarshan, Lindblad. And now, in the same vein as before, we can introduce controls here. The controls from the closed part, for example, fields or lasers influencing the system. In theory, one can also add a control to the Markovian part, to the system-environment interaction part, which in some applications is actually a thing. For example, open transmission lines, which can be coupled at will to a system, so you can have a type of bang-bang controls, like either 0 or 1, which can act as an additional source of control over the system. Of course, if that's not a thing, you can just say, well, gamma has to be constant 1, and there's nothing you can do about it. But this is the most, like the scenario where you have the most possible control over in this Markovian kind of setting. And this is, of course, useful because in the closed system part, we can only move on the unitary orbit of the initial state because we can only generate the unitaries. We have a Hamiltonian generator, but with this we can actually influence the eigenvalues of the system.
I'm sorry, can I make an extremely pedantic comment? But because you
please,
talk about like weekly, like weak conversions and so on. I mean, it's kind of interesting that that we know that the Lindblad form for generators of dynamical semigroups is like the most general form of dynamical semigroups in finite dimensions. But interestingly, that's not the case for infinite dimensional systems. There's kind of counterexamples where you can be in Markovian, like funny, like Hilbert Hotel type settings where you walk off to infinity in some way. But interestingly, they are like non-Lindblad form anticipators in the infinite dimensional setting. But of course, they're not really of relevance to any of this, in particular when you think of control. But just wow, that's my.
No, it's that's true. So usually one says that the semigroup has to be norm continuous, which in finite dimensions that's the only type of continuity because all topologies coincide. But in infinite dimensions, if one only looks at strongly or equivalently weakly continuous in the time parameter semigroups, then this GKSL form is not the most general one anymore. Indeed, so that's a pedantic yet I think important comment. If I claim that this is the most general type, then this is true to a large, but not like to the full extent, if you will. Okay, so this is the mathematical framework we're working in, and now the reachable set, which I just talked about, is also very intuitive. One has to be a bit careful what solution means, because if we say, well, we have L1 controls, what like is the path within the states we're getting that's not really differentiable, but almost everywhere. We'll not worry about that. We'll just take the intuitive idea of what a reachable state is. If anybody truly cares, we can go into the detail, but for now, let's just say this is the set. The reachable set until time large t is the set of all states which can be generated within that time. And then the reachable set overall just takes all possible t values. So in arbitrary but finite time.
And I mean, I'm aware of the fact that like time is a subtle matter here, right? That most of the time you can say that where you can go, but not so much on how long it will take. But of course, that's a perfectly meaningful definition. But of course, I mean, you can rescale time by redefining like the operator norm of the Hamiltonian and so on. So that's kind of meant in units of something, right? Like the operator norm of the Hamiltonian or like some norm of the Liouville.
Right. Yeah. So time usually needs some framework which depends on the actual setting you're working in. Admittedly, in this work, we only care about the reachable set for all arbitrary finite times, which this, of course, does not matter at all. But if
I'm not surprised because I mean, as we know, I mean, it's just extremely difficult to say anything meaningful on how long it will take, right? I mean, that's not a surprise. Okay.
Yeah, exactly. So yeah, for question of reachability, just can I generate the state in finite time, or approximately at least? This is what we'll care about. If one moves this one step further to optimal control, where one knows, okay, the state is in the reachable set, for example, but how can I reach it in optimal time or with optimal resources or whatever? Then, of course, this time parameter becomes important. But for us, we can, we take the freedom, the liberty of glossing over that a bit. Now, in terms of these control functions, I say I allow for arbitrary L1 functions. In practice, really, one only looks at piecewise constant functions, or that's the most widely used type of control functions, the piecewise constant ones, because these are easy to implement, as opposed to some arbitrary L1 function, which can look ugly as whatever. But one reassuring result is that the reachable set, if one looks at the closure, the topological closure, these two sets are the same because every L1 function can be L1 approximated by piecewise constant controls. To motivate why looking at the closure is reasonable, let's say we know that we can not generate some finite state rho f exactly, but we can approximate it arbitrarily well. And from the perspective of an experimenter or an engineer, that really is good enough because you always have other sources of error which prohibit you from reaching anything exactly anyway. Aside from the fact that exact, like what does it even mean? But that's a bit of a philosophical thing. But the point I'm trying to make is that from an engineering point of view, taking the closure is really all you care about, because if you say like this is the threshold I care about, if I get within this, like within a small ball of this final state, that's all I need really. So this is motivated by an engineering type of mindset, has the advantage that mathematically this is a much nicer structure to handle, as we'll also see in some of the results. So now one can write down this reachable set by means of some system semigroup, because admittedly we made a small simplification or some assumption that the Hamiltonian and the open dynamics are not time dependent in themselves. Of course, there can be setting where that's the case. Then the reachable set has to be defined a bit more carefully, because then the time parameter does play a role beyond just the control and how long you wait to implement something. But for us, we say the Hamiltonian and the dissipation terms are time independent. And then one can simply write down the solutions to this, and one knows that one gets all the reachable states by applying all the reachable quantum maps to your initial state. which if the dissipative part is controlled as well, one gets the full closed thing if gamma is 0, and the full dissipation thing as well if gamma is 1. So in a way, in this ideal setting of, for example, open transmission line, one has access to a whole bunch, a variety of unitary channels, as well as dissipative channels to influence eigenvalues. And this insight, while rather simple, will be very important later on when we actually prove some results regarding reachability. Now, the questions, we're looking at these open system control questions. Those are in general very difficult, and maybe you should start at least for a minute or two to look at, well, in the simplest non-trivial case, closed systems, what do we know there in terms of reachability? And those who are familiar with quantum control may have heard of the Lie algebra rank condition in finite dimensions, which just says if I have my Hamiltonian H0 of the system and all my controls, then I can generate every unitary channel precisely when the Lie algebra spanned by all these Hamiltonians is all of SUN or SUH, or now for general Hilbert space. So this notion of the Lie bracket here really means you take nested commutators and the linear span of this whole thing, and eventually you can just look at the dimension, right? And once you hit the dimension of SUN, you know, okay, I get everything, I'm controllable, I can generate all unitaries in this setting. In infinite dimensions, it's a bit more tricky, but we're okay with this result for now. Just it gives a rather simple criterion because this is just linear algebra, which is the whole idea of legal theory after all. A simple linear or algebraic condition on when I can, in a dynamical system, generate all kinds of unitary operators. This is very handy now in qubit systems, particularly. There one can use notions of symmetry. So one can show that controllability is equivalent to the joint commutant of some set. You don't have to care too much what this actually is, but the joint commutant to this whole set having dimension 2, so it being spanned by the identity matrix as well as the flip operator, as far as I remember. So for qubit systems, one has more than just this general Lie algebraic structure. One can also, one can actually use, kind of the symmetry of the underlying system. And there are no trivial symmetries which the controls cannot break in a way. So yeah, that's known in closed systems. Now for open systems, the situation is a bit more dire, admittedly. There's one very abstract result, which everybody who has heard of majorization will know immediately, namely that majorization on matrices, classical majorization on Hermitian matrices, is equivalent to unital quantum maps or unital dynamics. So as a simple result, if we only have unital open dynamics, so if all the Lindblad generators are normal, for example, then the reachable set cannot go beyond the majorization, not polytope in infinite dimensions, but this majorization set. So you cannot go beyond something that's majorized by the initial state. This is useful in principle in the sense that majorization is a simple criterion on the eigenvalues. The downside of this is that it becomes increasingly inaccurate the larger the system becomes. So this is really a theoretical or more like mathematical upper bound, which in practice, especially for larger systems, is more of a, we know that type of thing.
So you're saying that the bound is not particularly tight for large systems, or?
Yeah, exactly.
Okay.
As far as now, one can also quantify this in a way, but this, like off the top of my head, I wouldn't know what the exact result is, so I won't misquote anything. And now the setting, which I also teased a bit, is like we have noise, which is switchable. There, for a qubit system, if you have a fully controllable closed part, so this Lie algebra rank condition holds, we can generate every unitary in some finite time. It may take us long enough, but we can do it at least. Then one can show that if the noise is local amplitude damping, so one of the qubits of this qubit chain is coupled to for example, a bath of temperature 0, which then involves amplitude damping, then one can approximately reach every state there is from any initial state. Yeah, so in a way, in this qubit system or qubit chain setting, under these dynamics and the assumption that the coupling to the bath can be controlled, one can guarantee for arbitrary state transfer. So one can go from any state to any other state, at least approximately, and even constructively. We'll come to that in a bit, because we'll generalize this to arbitrary qubit systems. And we'll also show why this holds, like what the idea is behind going from state A to state B, even though we know nothing about state A and state B in general, because they're arbitrary, right? And now for this first setting, if we have a normal generator or a normal local generator, then in the same setting, if we can do the coupling at will, then we can exhaust this majorization set in the closure. Yeah, so it appears that that as soon as we have as soon as we have controlled dissipation and sufficient unitary control, that some of the at least in some sense the trivial upper bounds become equalities, because the separation of, oh, I can do a lot of unitary stuff and I can do a lot on the eigenvalues in quotation marks, and that's enough to exhaust all possibilities in terms of state reachability. That's kind of the intuitive starting point here.
Maybe an extremely naive question on this.
Please.
Well, it's and I know the answer, I think, but never mind. I ask it nevertheless. I mean, just to be sure. I mean, noise can help, right? I mean, the reachable set for dynamic semigroups will in general be substantially larger than that of the respective like von Neumann reachable set.
Yeah.
So in the sense, I mean, of course you're kind of, I mean, if you have like a Liouvillean with a Liouvillean gap, of course you're driven to the stationary state, but then you can on top of that use the control parameters, so you can reach more states and things.
Yeah.
Good.
Yeah, exactly. So if we say fully unitarily controllable, then we know we can go anywhere on the unitary orbit, right? And for example, in terms of majorization, we know we can also go anywhere in this majorization polytope in terms of the eigenvalues, or in this temperature 0 case, we can generate any set of eigenvalues approximately. So it really is the composition of the unitary orbit, as well as what can you do on the eigenvalues, which really comes together here in this setting. Okay, so immediately one can ask, as I also kind of teased a bit, I mean, these are nice qubit results, but how generally do they hold? Do they maybe fail if you go to Q-trits? Like what's happening there? Then this amplitude damping thing, can we go to arbitrary bath couplings, like positive temperatures? What can we say there? For the more mathematically inclined people, can we extend this to infinite dimensions, or the quantum optics people, or whoever? So these are just some of the questions one can ask. One can also go way beyond this and look at, for example, these reachable set questions, but for optimal control, looking at in simulations, like how good is this closure kind of thing actually, like how accurate is approximating arbitrarily well, on what timescales are we working? One could also ask these questions. These are the ones we'll focus on this first half of the talk. Now, the Markovian bath coupling, we can model if we have some Hamiltonian with the energy is being sorted, we just choose the basis, the diagonalization like that. Then motivated by the spin J representation, we can choose the sigma plus and sigma minus, the ladder operators, but we just weight them with some ominous sine and cosine kind of thing here. Really, one chooses these, if you will, thermal angles. One just chooses these such that the fixed point I'm running into the stable state, that just becomes the Gibbs state. So really one starts with, oh, I have this spin J representation, how do I have to tweak it in order for this to be a universal bath coupling if I look at it from the steady state of the system, from that perspective. And indeed, what one can show that with these two generators here, where T, I should say that T refers to the temperature of the system, which is a parameter. This does not mean the transpose, would be kind of pointless here. So then under these uncontrolled dynamics, we know that every state relaxes into the Gibbs state. So in this sense, we call it a bath coupling of temperature T, Markovian bath coupling.
So this is not unrelated to what people sometimes call a Davies map, right?
I think so. Yeah, I think you're right.
Okay.
Okay. Also for those people who know more about quantum thermodynamics, these dynamics actually constitute a Markovian thermal process. So this is not a thermal operation. I believe at least it's kind of hard to decide these things, but at least it's a thermal process. So the what that really means is that the dynamics of the diagonal of the state in the eigenbasis of H, the diagonal dynamics are independent of the off-diagonal dynamics. And later for quantum thermodynamics, if one also asked about reachability there, there was a recent paper on Markovian thermal operations, what one can generate, then these type of distinctions of what your dynamics fall into, like into which class, that becomes important. For now, for us, this is just a side note. For those who know what this means, they could be like, oh yeah, that's interesting. Right, now, keeping or recalling this thing, the separation between unitary dynamics and eigenvalue dynamics, which, because we have control over dissipation in our setting, can kind of switch in between. We can look at a simpler model for now, and later we'll see how that relates to our control problem right here. So what one can do is, of course, one can say, well, I have full unitary control, so I can always diagonalize the state. Whether that's useful or not, different question, but we could do that. And because we have this Markovian thermal process property, if a state is diagonal, it stays diagonal, assuming we don't apply a control at the same time. So if we just let the dissipation run, we'll not run out of the set of diagonal states. So one easier model one could look at is a toy model, which it's written kind of technically here, but really all we do is we have this the continuous time evolution, which is just the dissipation, the action of the dissipation on the diagonal. So we can let that run for some kind of time, and we boil down the unitary control we have over this diagonal system to permutations on the populations of the energy levels. So we can choose arbitrary time points where we say, like, for 200 milliseconds, we let the dissipation run, then we apply this permutation, and then let the dissipation run again, permutation, and so forth. This is the easier model we can work in, which admittedly, this is simpler to analyze, and everything I can do in this setting, or everything I can reach in this setting, I can also reach in the original system, right? Because this takes advantage of some of the things we can do in the like quantum control problem, but not all of them. Yeah. So in general, one will not have quality, but at least one gets this subset relation. Okay, and this brings us to the first result already, the temperature 0 case. So if we take the limit of the temperature to 0, then one of the generators will vanish and the other one will become the usual ladder operator. So these weights go to a constant. So the result reads as follows: if we have our control system such that we know we have a full unitary control, so the Lie algebra rank condition holds, and the generator is sigma plus, potentially just locally, so we could have a chain of qubits and just the last one is coupled to the bath, for example. Then one can prove that the reachable set in the closure, just like in the qubit case, is everything. So these dynamics, these control dynamics, allow for arbitrary state transfer. And the ingredients we use, and I want to pinpoint that, is that we have full unitary control and we can couple the bath at will. Of course, if we cannot do that, if we have no way to stop the dissipation, then this idea of I can generate all eigenvalues or all eigenvalue configuration or population configurations, that will simply break down. So unsurprisingly, this is important for this result right here. And the other nice thing about this result, other than this intuitive idea of, oh, I want to do state transfer, I can always do so in a Markovian way, at least approximately. So on top of that, this result, or the proof of this result, is constructive. And it will use two main ideas. The first one being, because we're unitarily controllable and we can turn off dissipation, we can always diagonalize rho 0 with respect to the Hamiltonian. And this boils down the problem to how can we generate all eigenvalues? That's really the separation I was talking about. So within the toy model, we have to show, given two probability vectors, how can we go from here to here, approximately at least.
So this is also where majorization comes in, right? And this whole convex structure and polytopes, because you're always mixing like extremal points in some way, and have to kind of find a clever kind of reasoning of what steps to take.
Right, exactly, yeah. There's this separation, because we can work on the eigenvalues independently in a way, at least in terms of this toy model. This is in a way, in a sense, why majorization comes into play, correct? Now, within the toy model, we have our two probability distributions, or let's say the initial state is here, the final state is here, with our simplex of probability vectors, in this case qubit, so a 2D like 2D triangle. And all we know within the system is we can cool to the ground state. So after infinite time, or in the closure, we can reach this corner right here, and we can apply these permutations. And now, how can we go from orange to blue? That's the question. And the important insight here is that the generator, so for now we have one qubit, we don't have a chain, but just one qubit fully coupled to the path, that the one generator we're looking at is of a nilpotent structure. So sigma minus or sigma plus is just the first diagonal next to the, or first off diagonal next to the main diagonal being filled with entries, everything else is 0. Meaning we have invariant subspaces. Yeah, so in this picture, if we are in the ground state, then we'll stay in the ground state. If we will go one dimension higher, if a state is in this edge of the polytope, it will stay there under the dynamics. And this invariant subspace or invariant phase idea, this we will use. And the universal control scheme, or the idea, is the following. Instead of going from initial, or from ground state, if you will, to the final state, what if we try to find our way backwards? Because in the final state, once we apply the dynamics, the dissipative dynamics with negative time, so we go backwards, one can prove that we will hit a phase eventually. So we know there exists a point on this phase down here, for example, which if I just let the dissipation run, I end up in here. Now this point, which has 1, 0, in this case, one of the population is 0, by means of permutations, we can swap into the phase, which is invariant under the dynamics, thus reducing the dimension of the problem by 1. And doing so recursively will lead us to the ground state eventually, which we know we can reach. Yeah, so in a way, we create this universal control scheme from two ends, if you will. Like we know that from the initial state, we can go to the ground state, and from the final state, we can go to the ground state backwards in time. So this is where they meet. This is how we get our final universal control scheme. Obviously, this for a generic initial and final states is not optimal. It's very far from optimal. So this is the price you pay for it being universal, that you can apply to any pair of states. So once one moves from reachability to optimal control, then the optimal control schemes will look nothing like that. But for the sake of proof and the idea that this is a constructive scheme one could apply in simulations or an experiment, I think this is really one of the selling points of this result, beyond this intuitive Markovian state transfer thing. And one can also generalize this as the theorem kind of states to local couplings to a temperature 0 bath with a similar idea. But this is really the takeaway message of this theorem. This is why this works. This is what's happening behind this behind the stage.
So how generic is this? Like for the type of, I mean, like how much does it depend on your choice of the Liouvilleans and Hamiltonians?
So this, or what we're using here, the properties we're using of the dynamics are, first of all, the dissipation into the ground state and the invariant subspaces, right? So the nilpotent structure of our system. As soon as we can guarantee that, especially the nilpotent part, the invariant subspaces or subsets, as long as we have that, then this should be a universal kind of scheme one can apply. And the ground state really, or in this case, the steady state is just the connecting step between the two, if you will. I hope that addressed your question somehow. I just made up some words and
yes.
hope they made sense. Okay.
Thank you.
Okay. Now this is the first result. I see I'm running way late on time, so I'll go a bit quicker to this through this, so we get to the actual thermodynamics part. Of course, the intuitive connection is that, well, we showed something for temperature 0 or local temperature 0 bath couplings. It's nice, but what if we have a bath of finite but positive temperature? What can we say there? And there's a result from roughly 10 years ago, or pretty exactly 10 years ago, which says that for qubits, or for a single qubit, one can specify the reachable set or the closure of it, of this system we're talking about. So full unitary control, which for a qubit admittedly is rather simple, and this switchable bath coupling. So here, unsurprisingly, the Gibbs state comes into play, as well as the initial state, also some form of majorization. However, this heavily relies on the qubit structure, and going to qubits, one can very easily find systems where this doesn't hold anymore. Actually, that seems to be the generic case. So this qubit structure of the majorization being a pre-order way I can always compare two states, because the eigenvalues for a qubit are just an interval, right? Or can be parameters by an interval from 0 to 1. The simple geometry allows for this result. As soon as we go beyond that, things become difficult. The second result, I'll simply state this for now, because we'll come back to that in the second half, or the last third of the talk, really, is that we have a bath of positive temperature, so modeled by these ladder operators with these thermal weights, if you will, to guarantee the Gibbs state being steady state, the unique steady state. Then for the toy model, one can prove an upper bound. Now, if you recall, we said that, or we saw that what we can do in the toy model, we can always do in the full quantum model as well. But the converse does not hold. So this upper bound suggests that there should be an upper bound for the original control problem we were looking at, but it does not transfer trivially. So we would have to put a bit of work into this, but at least if we say, we limit our unitary controls to some subset, then we'll get an upper bound. And the conjecture is that even if we allow for all unitaries, this will still hold, but difficult question. Really, the takeaway message from this result is that given some initial state and some Hamiltonian, some temperature, so there will be a vector of Gibbs weight, obviously just the eigenvalues of the Gibbs state. The upper bound is a classical majorization polytope, and the point which spans this upper bound polytope is one that has to majorize the initial state. Well, kind of obviously it's the structure of the thing, majorization, and one needs that the Gibbs state or the Gibbs vector and this vector z divided by d entry-wise, those are similarly ordered, or in a more group or algebra theoretic context, if we look at not this whole simplex but the wild chamber of ordered probability vectors, and we skew it a bit, so we get this Gibbs adjusted wild chamber if we just divide by d, or if we take d as a reference really, then this upper bound vector has to lie in this like skewed wild chamber. That's kind of the geometric idea. And the whole point is that, first of all, this vector exists and it is non-trivial, because of course I can always choose z to be a pure state, right? Then the right-hand side is just a set of all states, and this is trivial. There's no point in doing that. But if the initial state is a full rank, so there are no zeros in there, then one can choose z to be a full rank as well. So this really is a non-trivial upper bound. Really, one proves this by heavily making use of the convex structure, that this is a convex polytope, and if I know that at the corners the dissipation goes into the polytope, or at least points tangentially, then we know that we cannot leave this polytope in our control setting. So our initial state in there, and even at the corner, so at the edge of the polytope, we cannot go outwards kind of into it. If the computation is not trivial, but once you know how to do it, it's straightforward. And the existence of z, and this is really what the bridge to the second part will be, this comes via demajorization, or in physics known as thermomajorization, and the associated polytope. All right, one thing I didn't mention. For this result, you need the energies of the Hamiltonian to be equidistant, so in a way a spin Hamiltonian, if you will. And this result becomes wrong if this is not guaranteed. This doesn't mean that there's no upper bound anymore, just that this upper bound right here does not hold anymore. I assume, yeah, the example is just some numbers you crunch, and you see that if this is your polytope, your upper bound, then the pure dynamics in one of the corners just like goes like this. So immediately leaves the polytope and then returns to the Gibbs state. So not much intuitive insight here. This is just some generic numbers you crunch and see, yeah, this can't work in general. The last thing is the result of the normal generator. So, for example, bit flip noise is one type of normal generator, generates unital dynamics. And one can also show that this result of a normal generator, as long as V is not trivial, so as long as you actually have open system dynamics, then full unitary control is enough to guarantee that the set of majorized states is exhausted. Admittedly, this result is also interesting to show the strength of controlled dissipative action. The proof is not as nice because it is not constructive. It relies on the Schur-Horn theorem, which says if you have some matrix, then the eigenvalues always majorize the diagonal in an arbitrary basis, and the dissipation is just used to set all the off diagonals to zeros, and then you can reach everything that's majorized. Very briefly summarized what's going on here. So the dissipation part, again, is constructive, but the first unitary you apply, that one comes from a theorem of existence, which is not as nice, I guess. But this is one of the results. This normal result also holds in general. Now, one can go to infinite dimensions mathematically. Very interesting for some applications, very useful. We'll skip over that for now. Again, if anybody cares enough, I'd gladly come back for a 3-hour talk where I can explain all of this. But for now, let's just say one can do this in infinite dimensions. All of this works. One has to be a lot more careful with the notions, but one can come up with a mathematical framework where this result still holds. Okay. But back to the finite temperature setting, because this is where we go to thermomajorization for the last 10, 15 minutes, something like that. And most of this is a connection we've drawn rather recently. So this result of this theorem here, where you also, for existence of such a point Z, you need thermomajorization and the associated polytope. And there's actually a lot more structure that you can, that one finds if one really looks at this polytope, the set of states one can, or the set of states that are thermomajorized by an initial state. Okay, but step by step, really quickly, what is thermomajorization? Where does it come from? And really, the notion, or one of the notions this comes from, to be precise, are thermal operations. And one can also go to enhanced thermal operations or Gibbs preserving maps. In the diagonal scenario, these are all the same, but from the physical point of view, this is what one does. One has a system and a fixed background temperature, and now one defines a set of allowed operations which can be implemented at no cost. We'll just define them. We'll not go through why this makes sense in detail. Just for intuition, one uses the general, well, in a way, Stein spring dilation of that every channel has, and just restricts the ancilla and the unitaries to, so the unitaries have to conserve global energy. But using this Stein spring dilation form of the channels, one just says, okay, this cannot be fully general, but this has to be of this form, and this has to satisfy this condition, and then this is thermodynamically consistent. These transformations do not allow for work extraction. And now thermomajorization is defined via, I'll give it two states. I can go from state A to state B via one of these maps, or at least I can do so arbitrarily well. Again, from an application point of view, taking the closure, rarely a bad idea, at least for existence of such a transformation. Now, this set, the set of thermal operations, has a bunch of nice properties. It is bounded, path connected, and a semigroup. So compositions of thermal operations are a thermal operation. If one takes the closure, one even gets convexity and trivially compactness, infinite dimensions. And for control applications, these properties are the minimal structure you need, especially the semigroup structure, which is very intuitive. Like if I can apply operation A and operation B in a controlled manner, then the composition should still be in the set, right? It's very intuitive kind of thing.
But this is not a requirement. This is also basically an insight, is it?
Yeah. So it is good to know these things about the set or its closure.
Yeah.
And it allows one to say, okay, knowing this, we can safely go to some types of control questions without having to worry that we don't have enough structure. So that's why I wrote this here. Now, in general, as usual, very difficult problem. For the classical case, however, one can reduce this to a simpler condition. So if we have two states which are diagonal with respect to the Hamiltonian, then we can define something called something known as thermomajorization curves or Lorentz curves, which one can define rigorously. Usually they're defined via you reorder your vector like the vector z you're looking at, your initial state, and order it with respect to the Gibbs, the vector of Gibbs weight in some way, and then you take the like connecting lines between some 2D points. But mathematically, this is just a finite minimization problem. One can show this. And then one sees that in this classical case for diagonal states, thermomajorization is equivalent to comparing these thermomajorization curves. One could go into more detail and connect this to the mathematical notion of demajorization, so the existence of a Gibbs stochastic matrix, which maps the eigenvalues of rho to the eigenvalues of omega, and rho to omega, plus rho thermomajorization is omega, and a bunch of nice equivalent conditions, because in practice this can be kind of finicky to check, even with the ordering kind of thing. One can do this a lot simpler. One can also characterize these curves in a bunch of ways, and shows that this is the same as the definition in the physics literature. Most notably, a very simple condition to check is that the two vectors are for the same trace, and one has finitely many, namely n one-norm conditions one has to check, so that one can reduce this from a continuous problem or a semi-definite programming problem to finitely many calculations one can do. So just to mention, this is a thing, like there's a rigorous connection between the physics literature definition and the mathematics literature one. Okay, with this in mind, this idea of from some initial state, I can, in a thermodynamically allowed or thermodynamically consistent way, I can generate all kinds of final states. Let's take this idea of reachability and kind of apply it here. So given some initial state, in this case diagonal, because we know stuff there, given this initial diagonal state, let's look at the collection of all states which we can reach by means of thermal operations. And really this then boils down to this demajorization or thermomajorization curve criterion right here. Now what one can show is that this set, which really is defined in a rather arbitrary way, just or which may not look like it has as much structure, one can actually show that this is a convex polytope, and that this curve, this thermomajorization curves, contains all the information regarding the location of the faces, as I wrote. So as you all may know, there are two components to or two pieces of information to a convex polytope. First of all, the orientation of the face, so what is the normal vector, where is it pointing, and then of course at which point does the half space cut off what does not belong to the polytope. So this vector here, which is applied to the vector in the set, this gives the orientation, And this value here of this inequality, this gives the location. And the result is that, surprisingly, that the orientation of the face is completely independent of your system, like your Gibbs vector, your initial state. This is universal. Only the location of the faces, that one is influenced by which states and which system it shows. And precisely is then described by this thermomajorization curve or values on it. Now, another thing one can show is, because of this very convenient structure here, this orientation of the faces being described by these binary vectors, by these 0, 1 vectors. Because of this, all the extreme points, so the vertices of this polytope, are of a very convenient structure, and that's also known in the physics literature already. Namely, that these extreme points simply take certain values of the thermomajorization curve and simply take the difference. Mathematically, it just means that there's a simple structure to the inverse of such binary matrices, which constitute the extreme points of this polytope right here, very roughly speaking. Now, one can prove a bunch of further very nice properties. First of all, something that is physically very intuitive, or could be very intuitive. Mathematically, one needs to put in a bit of effort to prove this, but if I adjust the like the temperature slightly, or if I have slight error in energies, or the initial state is like slightly off, then this polytope changes in a continuous manner. So there's no jump of like, oh, I'm slightly off in the energies, discontinuous jump. This is not a thing. So in this Hausdorff metric, which is the strongest metric one can have for like compact sets, one has continuity in all these parameters. So physically, this is maybe kind of what one expects. Now, connecting to the control problem, I was talking about one of these extreme points, which we called Z previously, does classically majorize everything inside the polytope. And this point is unique up to permutation. This point we are looking for in the control problem, which tells us, okay, you cannot go beyond this set right here, this majorization set. This point, one can prove existence and properties if one goes to like this polytope H description of the polytope, so this half space kind of geometric description of the polytope. This is really the key in proving this, and it has the property 1, 1. So this is really the point eligible for the control problem. One can even specify when the initial state itself gives this upper bound. So this is the connection to what I talked about in the first 40 minutes. And another nice property, which if you look at some numbers is also not that surprising, is that the polytope always has dimension n-1, or it is singular. So what cannot happen in 2 dimensions if we're in this, like we are in our triangle in the simplex, and now we think of our classical majorization polytope, some hexagon, which is a 2-dimensional shape because we have 3 dimensions, n-1. What can never happen is that this hexagon degenerates to a line, to something 1-dimensional. If it degenerates, it has to degenerate into 1 point. Another result that comes out of the half space description. Okay, so that's kind of the framework we are setting. And now all this second part led up to really was something we were looking at because of this control problem. Because what one can do now is say, okay, I have this control problem with a temperature parameter. I know I have this upper bound for all temperatures, but how does this upper bound look like? Or like, how does this point, this specific point, which gives the upper bound, behave under temperature changes? And this is really the question we are asking at some point. And now I'll have to switch to here, this animation I've generated. I hope you can all see this.
Yes.
Okay. So what we're seeing right now is, again, we have a Q-trade system, a Q-trade spin system. So the energies are equidistant. And here's our Gibbs state. Right now we're in the high temperature limit. So this is just equal weights and some fixed initial state. So the setting now is the initial state and the Hamiltonian stay the same. The temperature changes. So what will happen is that the Gibbs state will, in a curved manner, go to the ground state for temperature 0. And we will look at how does the demajorization polytope, so this red set, how does this change with the temperature? And what one sees here, as D gets close to the initial state, it becomes smaller and smaller. Then at some point, you see here, this becomes a triangle, which is kind of weird. So from 6 corners all the time to suddenly 3. And then at some point, as soon as D overtakes the initial state, we go up here, and eventually we get this set for temperature 0. And especially, as I already said, this degeneracy behavior of some corners running through each other, to go back for a bit, you see at some point that this point will go through the initial state and even change direction. So it's kind of a corner type of thing.
That's cute.
And right, and one thing we asked is can one classify this behavior? Where does this even come from? Admittedly, this is motivated from this control question. I'm not sure yet, to be blunt, why one should care from a physics point of view outside of control, but we just did it anyway. And if anybody has any ideas why this is cool and interesting, feel free to say something after the talk. But so this degeneracy setting, there will be 2 answers to that, and this will really conclude my talk. This will be the final results of what I'm talking about today. So what we saw is that at certain temperatures, there are states running through the initial state, so these will coincide. And indeed, one can classify this. So when given your Hamiltonian and some initial state, one can explicitly write down the temperatures at which the initial state is a degenerate corner, so at which another corner runs through Y. And this really, it kind of looks like a derivative in a way. Really comes from the fact that some of the ratio of the population and the Gibbs weights, some of those have to coincide. Because this is where this comes from. One can show that this mapping I was talking about that maps permutations to extreme points of this thermomajorization polytope, this mapping outputs the initial state if and only if this permutation, when used as an input, sorts this vector y over d decreasingly. And of course, if 2 of these ratios coincide, then I have a degree of freedom where I can just swap these 2, so I can change my permutation, but this condition still holds, and y is still an extreme point, which I get as an output. Yeah, so really the condition, the equivalent condition is, as I said, this equality of ratios of population Gibbs weight. And if one just inserts the Gibbs weights for D, one can solve for T and gets this critical temperature. One should note that for generic Hamiltonians and populations, the temperature could become negative. So in a physical setting, this type of degeneracy may not even occur. So one needs that the energies in populations satisfy a certain ordering for this to be a physical temperature, a physical phenomenon that happens. But at least this situation where the initial state is a degenerate corner, this one can fully classify. And also this triangle behavior for a Q-trit spin Hamiltonian, this is also generic. So one of these critical temperatures here will yield a triangle if one has a certain inequality on the populations. So just to say, we just didn't pick very lucky with the Hamiltonian or the initial state. This is just something that happened. Nice result. Okay, but the final question I want to answer, and I know I'm already a bit over time, so thanks for bearing with me. So the final thing I want to ask is this the only type of degeneracy? Because if we were to look at this video again, or this animation again, the only thing that seems to happen is precisely that corners degenerate by running through this blue point. Other corners, like these two down here, for example, they coincide at some point, but that happens exactly when the blue corner is degenerate. Yeah. So what in this scenario seems to not happen on this animation is that the blue corner, the initial state, is its own extreme point, which is not so that this extreme point map is only produces the initial state once, but any of the other extreme points coincide. This seems to not happen here, but can this happen? And if so, when can this happen? And it turns out there's a state-independent degeneracy. There's a universal temperature at which the largest Gibbs weight is the sum of the two smaller Gibbs weights, or to put differently, the largest Gibbs weight is 1/2 if we normalize things to probability vectors. And this leads to a degeneracy on the thermomajorization curve, which really comes from a degeneracy in the Gibbs stochastic matrices, which, if we recall, those are another characterization of when this state transfer is possible. And there's a second animation I have right here. Here it is. So we start in the maximally mixed state. We ramp up our temperature. Now we see we have 6 corners, which is the maximum. There cannot be more than n factorial corners. And at some point, you will see that these two corners up here coincide, and they actually do coincide. This is not they go close, like exponentially close together, but they never touch. But indeed, for some temperature, like beyond this critical temperature, they are the same, they merge together. And this happens independent of what initial state one picks, always at this temperature. And one can prove, first of all, why this happens, and second of all, that this is the only other degeneracy that can happen. So the result says, if this polytope has degenerate extreme points, then at least for one of the following statements holds. Either the first condition where we showed this is equivalent to the initial state being degenerate, or in a way, the vector of Gibbs weight is not well structured. And I can, like, this definition is a bit technical, but one can visualize this very nicely if we have our Gibbs vector and we have weighted Gibbs weights, so D1, D2, D3. Then there are two situations how all of these are ordered. Well, first of all, D3 is here, that's the smallest one. D2, and for the thermomajorization curve, we also have to care about sums of these. So the largest one is then D1 plus D2, and the one next to that is D1 plus D3. So this one is set in stone, no matter what the temperature, what anything is. The degree of freedom here, and this is where the well ordering can break down, is that beyond this critical temperature, what happens is that the sum of these two, D2 plus D3, those are smaller than D1. So for low temperatures, where the largest Gibbs weight becomes closer and closer to 1, this is the ordering one can have. And keeping in mind that one picks two of these points for the thermomajorization curve, so one of the single D entries and one of the sums of the two, this ill ordering of the entries in D, this can lead to a degeneracy in extreme points. Very roughly, or very rough attempt to summarize what happens here. And as soon as one can guarantee that one has this like order structure that all the single Ds are like here, and only then all the sums of Ds come, and so forth. This is what I call well structured in this definition. Then one can only have this situation where Y is a degenerate extreme point. And so really just to summarize this result, either one has these critical temperatures where Y is degenerate, or one has this ill ordering structure where the Gibbs stochastic matrices have degenerate extreme points, and that can transfer to the thermomajorization polytope. Doesn't have to. The converse to this does not hold, because one can imagine like maybe I just take this point and at this point for the thermomajorization curve. So the curve doesn't really see how these two are ordered compared to each other. So in a way, this is necessary, but it's not sufficient. And this is really all I wanted to talk about in this context. One can classify this well-structuredness even more, and one can give a simple criterion on precisely when one is in this case. So when one knows if my temperature is above this critical temperature, then all that can happen is my initial state degenerates, and then precisely at these temperatures right here. So one can classify when this is the case just by the abstract solution to some equation. But really the takeaway from the second part, aside from this polytope idea and some of its properties, is that one can classify when one can classify the case when there are less extreme points than there could be theoretically. And one also knows where this comes from. So, okay, because I talked for so long, I think like 1 minute recap could be in order so everybody remembers at least partly what I talked about. So in the first part, I talked about open quantum control systems, like Markovian type independent dynamics, which one can influence by means of some external force. Maybe one can even control the noise, the dissipation. Then one can show that in terms of reachability, in terms of state generation, local coupling to a temperature 0 bar allows for arbitrary state transfer, so like local amplitude damping. For arbitrary Q-date systems with the universal control scheme. Now for finer temperatures, one gets an upper bound in the toy model, which is conjectured to hold in general, but not proven. And for normal jump operators, so for unital, not all, but some unital dynamics, the reachable set can even exhaust majorization, and the dissipation being controlled plays a large role in that. As a thermomajorization, one can analytically describe the demajorization and the associated polytope, and especially the extreme points by means of this curve and properties of this curve. So it's actually nice for just a small anecdote for looking for counterexamples that one can just explicitly write down this polytope in the corners. And at most one needs a calculator for some simple calculations, but one can do this fully analytically, which I think is a very handy insight and result. So this analytical description allows for a visualization, which is important for control applications with temperature as a parameter, for example. And one can analyze and fully characterize the case where the critical temperatures or where the corners degenerate. So in a way, there's less information required to describe what one can do in the system. And finally, which is the final and a rather obvious question, can one relate this notion of thermomajorization or generalizations of that to Markovian state transfer problems? And this is something I teased earlier, this idea of I have not thermal operations, but thermal processes. So something which has this coherent, like diagonal structure mathematically, which commutes with at h or at h, and which has the Gibbs state as a fixed point. So these types of processes, if one looks at those which are generated in a time-dependent Markovian setting, what can one say about reachable sets? And it turns out that in the classical case, one can define a continuous version of thermomajorization, which fully characterizes what one can do. So also very strong and interesting result, not one of ours, but one that came out, I think, last year. So yeah, what I want to say is that one can draw further connections between this thermomajorization and Markovian control problems beyond just this toy model or these specific bath coupling settings. Oh yeah, also there are a lot of open questions. Really, all I want to do is thank you for your attention, and I hope nobody fell asleep, and maybe there are some questions. Thank you.
Yeah, thanks for the talk. Thank you very much. So are there questions or comments?
Was everybody exhausted by talking?
I mean, I can start maybe. I mean, it's nice to have this kind of analytical form because then you can play games and so on.
Yeah.
So, I mean, you had these wonderful movies, but it was kind of not so clear, like what to do with it, right? I mean, because you get a kind of a temperature dependence, and it might, you're basically asking what way the temperature could matter here, right? Because the temperature comes in through the like Gibbs preserving maps, so that's kind of implicit. But then there's still kind of a temperature, right? And the reachable sets depend on this inverse temperature. So I don't know. I mean, maybe there's a point in like seeing to what extent like temperature can help, like a bit like in stochastic resonance where no noise is bad and too much noise is also bad, where there's kind of sweet spot in the middle. Maybe there's a point in like using thermality as a kind of a tool to reach other states or something. I mean, that might be some kind of like a hint at an application. Maybe and another thing, I mean, all the techniques are like majorization like, right? I mean, like Schur-Horn is like at the basis of most of this, right? Mathematically speaking. So I have two associations here. Like one is like they're a kind of symplectic analog. I mean, there's the symplectic version of Horn-Johnson. I mean, can one think of like this question of reachable sets in bosonic mode systems and then end up with again like these convex polytope structures? Does this make sense?
Right. So in principle, one has this Schur-Horn result like constant for more general Lie groups, right? And also this reachable set, or this idea of a toy model where you go to eigenvalues in a sense. One can actually generalize this to a huge variety of settings, like even mathematically to semi-simple Lie algebras and all that. So one can apply these ideas to further systems, if you will, especially with like the techniques generalized with the results depending on the system. They might not be as easy to attain, because again we also use some structure of the precise, or the actual generators we used, right? And or assumptions on the system, but just the mathematical framework, and it's some of the tools at least one can generalize to more abstract settings or more widely applicable settings. Yes.
And then maybe another maybe small mathematical point. There's kind of this Singh-Thompson theorem that kind of generalizes Schuh-Horn, like to like the same question, but for singular values versus main diagonals. I mean, like we given two vectors as inputs, and you ask whether there's a matrix compatible with one being the vector of singular values and the main diagonals being the other one. Is there an application for that in your setting when you think of Liouvilleans also, like non-Hermitian operators? Have you ever seen this ever in your setting, or is this a completely obscure point?
So I haven't seen this mainly because majorization for the types of bath couplings how we modeled bath couplings, that was never never came up. I feel like one can look at systems where that becomes a thing, because for like how's that if you have like what are the assumptions on the theorem again? Probably something with the one norm, right? Like that the sums of singular values have to be the same, and that's the one norm of some.
No. There's no constraint. It's just general. I mean, there's
that's general. Okay.
It's like a weak majorization that the sums don't the same. I mean, clearly, if you're not Hermitian, then the sums of singular values might be larger than the trace.
Right. Okay. I see. Okay, yeah, then that's a fair question, but I don't. This hasn't come up yet. Arguably, this is a somewhat small subsystem of control questions one can ask, right? So I wouldn't be surprised if this could be a thing somewhere. Totally.
Okay. Good. Is there any last question from anyone? So if that's not the case, then thanks again for this inspiring talk. That was great. And we catch up one-on-one later. And thanks all for listening. That was great. And see you later. Thank you. Have a good day.